and you are of course most welcome. This is Project Euler problem number 12, highly divisible triangular number. So a triangle number is just 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7. That's the seventh triangle number, which is 28. A 28 is the first triangle number with more than 5 divisors. It's got 6. So the question is, what is the value of the first triangle number to have over 500 divisors? So there is a quick way to find the number of divisors for any given n, and this is called prime factorization. So I did go through this on episode 3, but we'll go through it again. So let's start with n equals 28. We're just going to divide all the primes out of this number. So start with the smallest prime, which is 2. 28 does divide by 2, so we'll carry out that division. Now we want to store that value, so we've divided by 2 and we've done it once. So imagine this as a sort of dictionary. So we've divided by 2, we've done it once. So we divided by 2 to get 14. P is still 2. 14 does divide by 2, so we divide by 2 again. And then we add that there, so we've now divided by 2 twice. Now n is 7, and that's prime, so p will just increment, because 7 doesn't divide by 2, so p will increment all the way up to 7. And there we are. So we add 7, because we divide by 7, and we've divided by it once. 7 does divide by 7, so then n equals 1, and then we stop. Now, prime factorization of 28 can be written thusly: 2 squared times 7 to the power of 1. Now let's take a look at these exponents. So we've got a 2 there and a 1 there. We're going to add 1 to both and then multiply them together. So it's 2 plus 1 times 1 plus 1. That's 3 times 2, which is 6. So that is how we do, that's how we find the number of digits for n. So coding it up looks a little bit like this: def num divisors n. So we set p is 2. In fact, I'll make it d. D for divisor is 2, and we want a dictionary to store all the prime factors, so it's going to be factors equals the empty dictionary, while n is not equal to 1. So if n divides by d, then we either put d into the dictionary as a key with an initial value of 1, or we increment the value. So it's going to be something like this. If factors d, if d in factors, I think that's correct. Just having a bit of a think. If d in factors, if d in factors, sorry, I had to go and do something then. If d in factors, then factors d plus equals 1, else factors d equals 1. There we go. So that's what we do if d is a factor of n. If it's not, we got to do something else. Oh yeah, we've also got to divide here, haven't we? Divide n and d. There we go. So now we deal with the case where n does not divide by d. If n does not divide by d, then we'll just increment d. but we'll increment d cleverly. We won't just increment d by 1, because once we've divided by 2 and we're left with an odd number, that number will not divide by any other even number. So instead of going d equals 2, 3, 4, 5, 6, 7, we're going to go d equals 2, then 3, and then 5, 7, 9, 11, and so on and so forth. So if d is equal to 2, increment it to 3. In all other cases, increment it by 2. Right, so that takes care of the prime factorization. Now we're going to find out how many divisors the number has. So total equals 1. This is going to be a product, so we're going to take a bunch of numbers and multiply them together. So we're going to set total to 1 to start with. For k, v in factors.items, total times equals, and we take the exponents, which in our dictionary will be the value, and we add 1 to each, so v plus 1, and then we return the total. And we'll just see if that works. I will get rid of Chrome so we can have a look. There we go. Right, so print num divisors of 28, and we'll do a couple more of these. So 28, 512. And what was the number from problem number 3? I'll just have a look. Problem 3. That was a big one, wasn't it? 600 billion, 851 million, so on and so forth. So we'll have that there. Pop that in. Turn that back to problem 12. There we go. Right. So what have we got? So we've got 6, which is correct for 28. 10 for 512, which I think is also correct, and 16 for that big number, which I'll just I'll just trust the algorithm. Right, so that's that. Now we want to loop through all the triangular numbers until we find one that has 500 or more divisors. So simple way to do this: n equals 3, a equals 3, while num divisors of n is less than 500. So while the number of divisors for our triangle number is less than 500, we just keep generating the next triangle number. So n plus equals a, and a plus equals 1. And then we print n. Okay, so I think this is going to work. We'd like to see how long it takes as well. So from time import time, and s equals time there, and down the bottom time minus s. So this should work. Took a while, 3.98 seconds, as you can see. 3.98 seconds, so yeah, a bit slow. And there are all kinds of improvements we can make on this. This is the brute force solution, of course. We're starting very low with very small triangle numbers, and it's pretty obvious that you're going to have to start pretty big. So we're looping through unnecessarily a lot of triangle numbers that obviously don't have 500 divisors. So let's look at a few optimizations. Okay, so here's an optimization that should speed things up pretty quickly. So instead of starting with the second triangle number and then wading through a whole bunch of numbers that obviously don't have 500 divisors, why don't we just find the first number with exactly 500 divisors. Find out roughly where that is in terms of the index of triangle numbers, and just work from there. So something a little like this. So here's how to find the lowest number with exactly 500 divisors. Quite simple. We're going to take the prime factorization of 500. So 500 divides by 2 to give 250. That divides by 2 to give 125. That doesn't divide by 2 or 3, but it does divide by 5 to give 25. That divides by 5 to give 5. That divides by 5 to give 1, and then we're done. So this is on the right hand side is the prime factorization of 500. Now here's the clever bit. We are going to subtract 1 from each of these. 1, 1, 4, 4, 4. We are then going to write out, because we got 5 factors here, we're going to write out the first 5 prime numbers. 2 times 3 times 5 times 7 times 11. We are now going to give each of our prime numbers an exponent. So we're going to start from the bottom and assign left to right. So start from the bottom, 4. So we have 2 to the power of 4. We have another 4, 3 to the power of 4. We have another 4, so it's 5 to the power of 4. Then we have a 1, so it's 7 to the first power. And another 1, so it's 11 to the first power. And that is our starting point. That is the lowest number with exactly 500 divisors. Okay. So where is that roughly? What would be the nearest nth triangle number? There is a way to work this out. So let's say we have a much smaller number, 35, and we want to know where is that roughly in terms of the index. So is that like near the 8th triangle number or the 7th triangle number? Let's see where it is. So 35 equals, and let's write out the formula for a triangle number, which is n times n plus 1 over 2. Now some of you mathematicians will recognize that this is a quadratic formula. We just have to rearrange it slightly. So let's multiply everything by 2 to get 70 equals n. I'm going to multiply these brackets as well while we're here. So n squared plus n. Let's move the 70 over to the other side. So we'll have n squared plus n minus 70 equals 0. Now all we've got to do is solve for n, and we do this using the quadratic formula. Quadratic formula looks like this. Minus b plus or minus the square root of b squared minus 4ac over 2a. I'm just going to check you can actually see this, otherwise I'm completely wasting my time. You can see it, that's good. Okay. That's the quadratic formula. So what in blue blazes are a, b and c? Well, that's pretty easy. C is just the free term there, minus 70. B is, I forget the word for this. How many n's do we have in our formula? In our equation? We have one n, so b is 1. We also have 1n squared, so a is also 1. We feed those into the formula. So minus 1 plus or minus the square root of b squared. 1 minus 4 times a is 1 times c is minus 70. So minus 70 over 2a. A is 1, so bottom is just 2. So I should say denominator is just 2. Okay, so that gives us minus 1 plus or minus the square root of 1 minus 280. That's 1 plus 280, which is 281 over 2. Now, 281 is roughly 16.7. So I'm going to round that up to 17. Minus 1 plus or minus 17 over 2. So these are the two possible solutions for n. N is a square number here, so there has to be two possible solutions. So minus 1 minus 17 over 2 is minus 18 over 2, which is minus 9. And minus 1 plus 17 over 2 is 16 over 2, which is 8. Now obviously the positive number is the one we're interested in, 8. So according to our calculations, 35 should be close to the 8th triangle number. Let's see if that's correct. 1, 3, 6, 10, 15, 21, 28, 36. Right, stop there. 1, 2, 3, 4, 5, 6, 7, 8. So this is what we're going to do. Well, we've already done that. Find the first number with exactly 500 divisors, and then find where that is in the index. Like, what's the next nth triangle number? So here's how we're going to do it. I'll get rid of this, and we are going to start. So the starting value was 2 to the 4th times 3 to the 4th times 5 to the 4th times 7 times 11. There we go. So that's the starting value. Now we need to find the index. So where is this in the pantheon of triangle numbers? Why is that crashed? Oh no, it just... Okay, right, so index, this is going to be really complex, so I'm going to have a little think about this. We're going to have to import... Oh, I've done that. Square and ceiling. Then we're going to have to... oh, what are we going to do? So I want to get the discriminant first because I think this is going to make things easier. Discriminant. So that's the bit under the... Oh, I'll show you. The discriminant is this bit. Oh, sorry, I'm not showing you, am I? Is this bit here underneath the square root sign. That's the discriminant. So we'll do this. So it's going to be 1 minus 4 times minus 2 times that 1. Oh, bloody, I'll write this out. So it's 1 minus 4 times minus 2 times the starting value. So it's that. And it doesn't like it entirely, so we'll do that. Oh, it's not happy, so I've got too many brackets going in one direction here. Invalid syntax. Oh, yeah, it's supposed to be that way. There we go, so that's okay. That's the discriminant, and then index is going to be... What is that going to be? It's going to be minus 1 plus the square root of the discriminant divided by 2, but I would like to round that up. So it's going to be the ceiling of all this. And why doesn't it like that? Invalid syntax. Oh, we got too many. It's the other line, isn't it? We got too many brackets going that way, and not enough going that way. That's all right. So it was the line above. Right, that's done. So we found the starting value, and we found the index. So now we'll start our search from there. So, oh, excuse me a second. My mouth is a little dry. I'll just have a sip of Coke. we'll continue. Right, so while true, and we're going to move on to the next index. So index plus equals 1, and then if, oh no, we need to set up the triangle number. So t equals index squared plus index over 2. There we go. Make that integer division, actually, that's going to be easier. And then if num divisors t is greater than or equal to 500, then we have found the answer. We'll print it out. So we print t, and we'd like to know how long it took as well. So time minus s, and then we break out the loop. We don't need to do anything else. I'm going to see if that works. Should do. So I'm actually going to take away the Chrome and let you see how long it takes. Now bear in mind, the original algorithm took, what was it, 3.9 seconds? Let's see how long this takes. So let's get rid of the Chrome. Oh, something's crashed. Oh, what a bloody time to crash. There we go, right. Is it running? No, it's not running. Run it. And that found it in 0.785 seconds. That's quite a lot quicker. Let's try it again. 0.81 seconds. Okay, so we can speed this up a bit more. There's one other optimization. So we're going through all these triangle numbers. I think it's a fairly safe assumption that even numbers have a lot more divisors than odd numbers. So what we're going to do here is add a little condition. So if t mod 2 is not equal to 0, then we're just going to skip. We're just going to do continue. Otherwise, we'll do all this. So we'll just indent that. Run it again, see how long it takes. 0.34 seconds. That's about as good as I can get it. So yeah, that is pretty much it for episode 12. And that was a long one, wasn't it? Goodness me. Thank you very much for watching. I'll see you next time for a very short episode 13.